Hello everyone, welcome to this new tutorial on big data. So with this particular lecture, we are going to start a series on big data thing. In this first video, we'll talk about how to get started with the big data. So let's try to see what is the agenda that we're going to cover with this one. But before get started, let me quickly introduce myself. So I am Vishwa Mohan and I bring with me close to 9+ years of experience. And during this last 9+ years of experience, I get to work for the different companies. Like I started working for Oracle, then I have worked for PayPal, sometime for the Amazon, Walmart Labs, and currently I work for the world's largest professional network, which is LinkedIn. I'm a pass out from IIT BHU, and I hope with this my 9+ years of experience working in the different pillars of this IT industry, I will be able to bring some value to you folks, and that is how this tutorial is all about. Let's move on. So basically the idea of this whole tutorial is to give you a good transition from the old ways of storing the data to thinking in a big data way. So this whole session is planned around how you can transition from the old ways of storing the data to the new world of big data. So we'll try to basically focus on three things. One is why do we need the big data, second is that what big data is, and the last one is that how do we achieve that. So in the last we'll try to talk about the how part of that big data. But before I get started, I would like you guys that if you like this course, please do go and see in the description, and please register to the link, register to the courses on the upGrad. I think it will be really helpful for you guys, and the upGrad has been coming with the great courses. If you really like this one, please go down and please hit the subscription thing and please visit the link. Let's get started. So if you see, on a very high level, if you any computer, any laptop, any mobile as such, on a high level, they do only two things. Okay. On a high level, if I have to say, right, any laptop or any computer as such, they basically does only two things. The one is storage of data. Okay. And the another one is computation of the data. Okay. So whether you are having a mobile phone or whether you are having a laptop, any system as such, on a high level, you will be doing only two things with it. Either you are storing the data or you are doing computing the data, right? And data as such, these days has become so common that everyone is talking about the data. They're talking about data-driven decisions. People are saying the data has become so new while, but it is not something which is new. The data has been there for over a period of time, and from that time itself, say like 30 years from now or like 20 minutes years from now, that time also we used to do the same thing. Any system, any laptop, any computer, any supercomputer, any server, right? Normally they do only two things. One is the storage of the data, and another one is the computation of the data. Okay, I hope this is clear. The problem starts happening when you try to store beyond a certain limit. So for example, let's say initially suppose this laptop has a memory of say 500 GB of data. Initially suppose the system has like 500 GB of data, and soon that suppose that application or the website became more and more famous. So this now so I have a system like this which has a storage of 500 GB of data, but because more and more users have started using it, right? The amount of data that I need to store now is suppose say 600 GB. Okay, so now when it is a 600 GB demand has come up, the very first natural thing that comes to our mind is that what we can do, we can go and increase our storage capacity, we can increase our configuration. So the person sitting here will jump to the market, and in this market guy, he will go and say that, okay, my system is running out of space, what should I do? So this genuine guy will suggest him that, okay, there is some solution available with me, so I have some additional hard disk. What you can do is that you go and add into it. It will cost you something, but your system will get upgraded. So this person takes his hard disk and convert that into say 500 GB more. So this now becomes 1000 GB of data. Okay, now it was all good and fine for the initial things. What if this became further famous? So more and more people have now started more using it, right? So over a period of time, even now my demand has grown to say like 1200 GB. So even still when now it has become 1000 GB, I'm still not able to do up the things. So what happens in that case? This can again go to this person and say that, hey, my demands have again increased, what should I do now? So this person will say this, okay, there's another new hardware that you can go and add into your system, and your system will scale up, right? So this kind of changes in which, in order to scale your system up, in order to start supporting more and more load, in order to support more and more requests that is coming in, whenever you keep improving your system, you keep improving the configuration. That is known as the vertical scaling, right? So for example, in this case, I have one server, but in this server I just wanted to add more power to it. Maybe I add more processors, I use better networking gears, add more storage to it, right? So I'm just vertically scaling it. So this kind of way to solve the problem of the storage, the one thing that we can directly do is known as the vertically scaling. So this is also known as vertically scaling up. So what we are doing is that we are just adding more and more resources to the same server, and we are bringing the server up. This is known as vertical scaling. But what happens is that practically speaking, there's a practical limit to which you can vertically scale a system. So for example, initially your machine had like 500 GB of data, okay, and you increase it further, vertically scale it, and now you made it like same machine you have made it like 1000 GB, right? And then again, suppose the need determined, and you will further increase it to say like 2000 GB. Okay. But if you keep on doing it, there's always a practical upper limit to which you can go and vertically scale a system. So that is one one of the limitations was that limit to vertically scale. This is one limitation. Okay. The second limitation is that people try to do some observation. They try to plot a graph between increasing capacity. So they were increasing the capacity of the machine, and on the y-axis they were trying to plot the performance. What they saw was initially with the increase in the capacity, the performance was improving, but after that time it started plateauing. What it means that initial some period of time when you were trying to increase the capacity, the performance was getting up, but beyond that limit, what happens? The performance plateaus. So again, this gave us a clear identification that I understand that if you can increase on capacity, your performance will improve, but that will always not be helpful, because beyond a limit, it has a limit. The third thing was that there's a very famous proverb: you should not put all your eggs in the same box, right? You shouldn't do all the investment in one portfolio. The same thing here. If you just keep on adding more and more resources to the same single machine, you don't know, right? There's so many failures can happen, like a power can go down, the hard disk can fail because of too much of load on a single machine. The CPU utilization is also getting very high, right? So it's quite possible that single machine itself goes down, right? And that itself can be a single point of failure, right? So the vertical scaling also has a problem which leads to the single point of failure, or single point of failure. So in order to avoid these kind of problems, what the next set of people suggested was that instead of having one machine, why don't you have the multiple machines? So for example, right now I have a machine of say so right now I have a machine say say like 500 GB. Okay. So instead of increasing the capacity of this machine, instead of vertically scaling it, what I'm trying to you make use of 4 machines of the 500 GB. So this one is 500 GB, this one is 500 GB, and this one is also 500 GB. So this kind of scaling opportunity, in which what you do is that you increase, instead of using one machine, you are taking the n number of machines now. This concept is known as the horizontal scaling. Now this started solving the problem which the vertical scaling was bringing, because practically speaking, when you are if the more and more nodes, more and more load is coming, what you can do is that you can just increase the number of nodes, so that will increase your cluster size, so it is easily scalable, right? And also if some of the nodes goes down, then also there are other nodes which can serve the load. So again, it is not a point of there's no contention of single point of failures. So because of these two reasons, people started feeling horizontal scaling is the way to go instead of the vertical scaling. So I'm again repeating, the vertical scaling is done when you have a system in which you keep on increasing the configurations to make that system work. For example, if the storage capacity is going out, you add more storage layer to it so that you can store more and more. But if you continue with the vertical scaling, there is always a limit to which you can vertically scale a system. Also, we have seen that with the increasing capacity beyond a certain point, the performance starts suffering. And thirdly is that since the vertical scaling is only one system which you are scaling up and up and up, so it's always a single point of failure. To come up with that, there was another concept in which people started using, instead of single machine, they have a group of machines now, and this is known as the horizontal scaling. And this is basically a base of distributed computing also. And in other words, if I have to say, it is basically a fundamental base of a big data world as well. So we'll be talking more about the horizontal scaling in the coming slide, but just now, to just understand as of now in a nutshell, when we, instead of a single machine, we try to take up the multiple machines to do the same operations, that is known as horizontal scaling, and it helps to scale seamlessly, and at the same time you don't have any single point of failure. Let's move on and discuss more about it. So as I said, no, this horizontal scaling laid the foundation for a distributed computing. So what is a distributed computing, guys? In very simple words, if I have a single computer, okay, so a distributed computing is basically able to solve a problem which cannot be solved by a single computer itself. Also, any computer has basically two kinds of problems to solve. One is of the storage, right, as we already discussed, and another problem that any computer has to solve is the computation. Okay, so out of these two, storage and the computation, when you have such amount of data to store and you have such huge amount of computation to be done which cannot be done on a single machine, that is when the distributed computing comes into the play, or basically you horizontally scale your system. So right now, as you can see in this diagram, instead of a single computer, I'm trying to divide that into the multiple machines. Okay, and these multiple machines are distributed, but they're connected to each other over a network. So all of these machines, as you can see in this diagram, now they are distributed. They are doing the work of a more than, instead of a single computer, we are getting the work done from the 5 machines, 6 machines as of now, and they're connected over each another, and this is also known as the cluster of machines, or nodes. So what we see, that we have been trying to solve a problem with a single machine, we have been not be able to do it. We first tried to vertically scale it, that was also not possible. So we came up with a horizontal scaling scheme, and that is what is known as this, which has, it has distributed computing into the core, in which we try to solve a problem which cannot be solved by a single computer, and the problems are related to the storage and it is related to the computation. So this is what the basics of distributed computing is. So guys, what happened in the early 2000s, right? In the early 2000s, when the relational databases were at the boom, like, where the people were mostly using MySQL, Oracle, everyone was talking about the transaction. Few of the companies were actually struggling with the amount of data that they wanted to store, right? And that is when the initial proponents of the distributed computing, they, forwarded this idea that, okay, this is the concept that distributed computing brings to the plate. But initially, in the theory, it appeared that it will solve all the problems of a monolithic system, or a relational database kind of thing, in which you cannot scale them very easily. On theory, it looked very great, but as and when they started adopting this distributed computing, they were highly demoralized. And we'll see in the next session why. What are the challenges with the distributed computing? What are the problems with the distributed computing is? So as we saw in the, as we talked about that, instead of this single computer, right? We have been trying to solve the problem with, instead of a single computer, we have been trying to, there's a single computer this. And instead of this single computer, we have been trying to solve the same problem with the help of multiple computers, right? Like this is the multiple computers, and these are connected over a network. Okay. So now what happens in a distributed computing is that, if you have worked in a IT industry for a long time, or maybe, if you're just in the college and maybe you'll go and work in the IT industry, one thing that you'll realize is that network is one of the most unreliable thing when you have to work in the IT industry, right? There's always a chance that network can go down. There can some network glitches in the system, right? Maybe your NIC card is not working, or the network is slow, or the machines are not disabled to each other, right? So one of the biggest challenges in distributed computing is that, one of the machine getting out of connection with all the other machines, right? What happens is that one of the machine is not reachable by all the other machines. So for example, say it has to support, say like, each of the machine was storing, say like 30 GB of data. This is also storing like 30 GB of data. This is also storing like 30 GB of data initially. right? This is also supporting 30 GB of data. This one is also 30 GB of data. Now if suppose there is a network partition happening here, right? So if suppose there is a network partition that happens here, and this machine is now no more reachable to the other machines, right? This connection has been lost. Now what it leads? It leads to the loss of 30 GB of data, right? So what happens is that in the distributed computing, since network is one of the most reliable thing, and since machines are connected to each over the network, if the network goes down, if there's some glitch in the network itself, then what we'll realize is that the machine itself goes away. So one of the biggest challenge with a distributed computing is that network partition. Okay, so what is the network partition? Since in a cluster of machines, every machine is connected to each other over a network. If network goes down or it goes slow, some network glitch happens, one of the machine will not be able to connect to all the machines. So that may lead to some kind of data loss. That machine is unreachable, so I may not be able to query data or store data or retrieve data on that particular machine. So I may lose the amount of data that is there on that particular machine. So one of the biggest problem is the network partition. Let's talk about the another thing. As I said that in the case of the horizontal scaling, right, in which what I mean is that instead of a single machine, I go and use the multiple machines. Normally, the configuration that we use is very simple. Okay, the configuration that we use is basically a commodity hardware, a community hardware, which is not a very high stats or very high configuration. So as a result of which, since it is not very high end machine, the chances of the failure of those machines is again very high. So that is another problem with the distributed computing, since these nodes are very trivial, very normal nodes. So these nodes, chances of failure is very high. So normally what happens, another problem is that node failure. Okay, so the another problem with the distributed computing is that since the nodes are very, low configuration thing, they're not very expensive, they're not very specialized, so their chances is always, the chances of the failure is always very high. So normally, whenever the first time this distributed computing came into the place and people just jumped over it, started using it, these were the initial very frequent problem that they started observing into it. How the network was behaving, advertently. So that is why one of the nodes were getting out of the rotation. It was not into the network connected to all the other nodes. The another problem was that node failures was very frequent. So there lots of failure was happening because of it. Okay, the another problem was that it was very complicated system, setup was complicated, right? Just think, initially to do the thing you just have to set up one machine and set up one computer. Itself setting up a single computer is still a tedious task. Now just a single computer, you have to replace it by 10 different computers, and every computer has to be connected and network to each other. They have to be continuing talking to each other, right? So these all things added to the trouble, and these were the basically very high level challenges with any distributed computing is. So as soon as people started looking at these kind of problem, which was the network partition, node failures, setup was complicated, people were not understanding it, they started giving up their hands. Okay, so the first initial release of distributed computing, when that came to the people in early 2000s, because of these problems, the people started hesitating, in whether should I go with the distributed computing or not, because now distributed computing was solving initial problems of single point of failure. It was trying to solve the problem of scaling up the systems, but again it has its own unique set of new problems, like any node can going down at any time, network partition, setup was complicated, right? And not only that, right, since everything is now talking over the network, so it also resulted in added latency, right? And everything has been dependent on that, so much of dependency, network dependency. So the distributed computing, though it builds lots of things, but it brought its own sets of challenges. And at that time in the early 2000s, these challenges were so big that people started become apprehensive of using it, right? So in order to solve this problem, at least these two big monsters, right, the first two bigger problems, which is the node partition and the node failure, this has to be addressed first. So in the next thing, in the next slide, let's try to understand how can we address these two problems of the network partition and the network failure. Let's try to see that out. So now we see the biggest two problems. The two biggest problem in this case was of the problem was of network partitioning, and the second problem was of node failures, and both of them resulted into what? Loss of data, right? Because of all these things, the main thing that was happening was we were losing data, right? We were losing data, and each of them were connected over the network like this. So what the proponents of the distributed computing, what they said that both of these can be solved if we do one thing. Okay, and what was that thing? Can you guys make a guess? So people said that, okay, I understand there is a problem with the distributed computing, and the problem is because of the network partitioning and network failures, and both of them result into something called loss of data. Okay, and this loss of data is happening because I'm having only one copy of data. So what can we do? Can we replicate the data, or can I bring redundancy into the picture? Okay, and then this concept got highlighted, and this is what that is replication or redundancy in the data. Okay, what is that? Replication or redundancy in the data. So what it said is that it says that instead of having one copy of data, right, instead of having one copy of data, please go and store the multiple copies of data. So for example, if I have a data D here, and say I have a replication factor of 3. Okay? The meaning of the replication factor of 3 is that one data will have the 3 copies. So there will be 3 copies of a given data. So one copy is the original copy, right? And if it is a replication factor of 3, so it will have 3 copies. So suppose one copy I make it on D1, D copy 1, D copy 2, and maybe another copy here, D copy 3. So if I have a 3 replication factor, it means for one copy of data, I'm making 3 additional copies. So with bringing of this redundancy, with the bringing of this, replication factor is 3. It means that, even if 3 nodes fail, right? So even if 3 nodes fail, for example, if this also fails, suppose this also fails and this node also fails, still I'll have one copy of data, available. So what it means is that if we have a replication factor of say k, it means that for a given node there's k additional copies. So if I have a replication factor equals to k, it can tolerate failure up to the k nodes, right? So now this bringing the redundancy and the replication into the picture solve both our problems. The problem which has been created by the network partitioning and the problem that has been caused by the node failures. And what was the problem? The main problem was the loss of the data. Now since the data is replicated across the multiple nodes, even if few of the nodes goes down, we still have some another node which is having that data to serve that data to the end users, to end customer. So there's no loss of data that is happening. So the more number of copies we can make, the more guarantee we can give to our customer that okay, whatever happens, we will not lose your data. So for example, if the replication factor is key, it means that it can tolerate up to the failure of k nodes. Okay, so this brought a lot of confidence in the people. People again started believing on this this distributed computing concept, because now they realize that even if the node will fail, even if the network partition will happen, still there is a chance that my data will not be lost, because we are bringing replication and the redundancy into the picture, right? But that was not over. There are again few challenges with this approach also, and let's try to see it into the next one. So what are the challenges with this? So what happened is that I know what I did was that I added a replication factor. Okay, so I did a replication factor of say 3. Okay, and then what happened is that suppose these are data here. I made a first copy of data here, DC copy 1, data copy 2, and maybe data copy 3. Okay, so now what happens? The same data D, which has to be written in 3 different places. This one, and this one. So for example, just think of a consumer. Okay, and for this consumer, he wants to write some data. So whenever he has to make a request to write data on suppose this machine, right? This machine has to then forward this message to this machine also, and it has to forward the machine message to this machine also, and it has to forward the message to this machine also. And only when they all return success to this machine, that okay, I have written the copy, this also returns the message that okay, I have written the copy, and this also returns back that yes, I have written the data that you wanted to meet, then only this machine can return back the response to the user that okay, the data has been properly copied. Now this, if we do this kind of design in which a user will have to wait for the data to be written on all the different machines, and again these machines are not co-located, they are into the different zones, that is different parts of the world connected over a network, this client will have lots of, lots of waiting time. This client will have a lots of waiting time, which again is, these days the only thing that we don't have is time. Time is one of the most precious thing. Nobody wants to wait. We want to, serve our customer as fast as possible. So again, this is a big challenge. I don't know whether this, client will be happy enough, to wait for a long period of time for the response to come, right? So that is one of the challenge. Now to mitigate that, what other people suggest is that do one thing, whenever a client make a request. So for example, there's another client, and it's make a request to D1 for, to write some data D1. You write it, directly here, but all the things, all the writes to the other machine, you try to do asynchronously. So that thing that you see in the dotted lines, it is trying to write to the another machine in the asynchronous fashion. Asynchronous fashion. What is the meaning of asynchronous fashion? That it is not blocking call. So for example, as soon as this user requested to write D1 data on machine 1, as soon as it's written on the machine 1 itself, the response will come back to that user. And this user will be happy that, okay, yes, my data has been written. But the copying of this data, to maintain the redundancy, to maintain the replication, that will be done asynchronously. It's not be done the same time, but maybe after that time there will be some kind of sync job that will happen, which will replicate the data across the machines. Now, what is the problem with this? Suppose at time t1, suppose this is the time t1 when this user is trying to write the data. So d1 data was written, and suppose the time t2, there's another user here, and at the time t2, he wants to read the same data, and his request went to this machine. Now at between time t1 and t2, suppose this write has yet not happened. The write has yet not happened. So this user will not get the data, okay. And if suppose that was an update query, it will not get the correct updated data, okay. So what I'm seeing is that since there is a replication happening between the multiple nodes, right? So this machine is at a given instant of time, this machine will have some data and the another machine will have the another data. The problem is that the data is not consistent. Like this node has some another copy of data, right? And this node has some different copy of data, and this node will have a different copy of data. Or maybe at all this data node will have the data, but the another node which is supposed to have data is not having that data. And this is known as the, the consistency problem. This is known as the consistency problem. So what is the consistency problem? Whenever we try to store more than one copies of data on the different nodes, right? So suppose I have a replication factor of 3, and for each copy of data I want to store onto 3 different machines extra. It might be possible that we have not been able to update data on all the machines on time. Until the time everything is not updated, it will show some kind of consistency problem. One of the machine can have some other data and another machine can have another data. And this might confuse the client, and that is also known as the dirty read. Okay. So for one of the client, if they go and hit, so if there's a client 1, if it goes and hits another value, say 5, and if it tries to hit the another machine the same time for the same resource, it may get the value as 6 as the more latest updated data. So this is known as the dirty read, and this happens if your consistency is compromised. But one thing is for sure is that, since there is a asynchronous mechanism applied here, at some moment of time in the future, all the nodes will get consistent. What is the meaning of all the nodes will get consistent? The meaning is that all the node at some instant of time in the future will have the same data, and this is known as eventual consistency. So this is the term, and this actually sends the the basic of another important theorem, which is known as the cap theorem. So we'll be talking about the cap theorem in the next slide. But we have to understand now what is the eventual consistency. So the consistency means a state in which all the nodes having the copies of data, they all have the same copy. So this is known as consistency. If it is a strong consistency, it means from the beginning itself, right? Every node will have the same data, right? And if it is not very strongly consistent, it will be eventually consistent, in which there will be some period of time, between, till the time when every node gets eventually consistent. If a user try to read multiple times, he may get two different values, and that is known as the dirty read, the problem of dirty read, right? So with this said, we'll try to understand another theorem, which is a cap theorem, which is a base for any kind of distributed systems, and we'll try to read about it, what it is, and how it makes so much of sense to understand about the cap theorem whenever we are talking about any distributed system. Okay, so let's talk about the consistency cap theorem. So the cap theorem, what it says that if there is a distributed system, okay, if there is a distributed system, and if there is a distributed system, there can be, you normally try to have three kind of problems you will have. Okay, so the three kind of problem that you have is, one is that failures. The failures can be because of the network or the node failures. Okay, and the second one is the availability issues. And the third one is known as the consistency. Okay, so what it says that cap theorem state that out of these three, the failure, availability, and the consistency, you can only achieve two at a time. You can only achieve two at a time. So either you can achieve the failure, control over the failure and the availability, and you have to compromise on consistency, or you can achieve the consistency and availability and you can compromise on the failure, or you achieve the failure, control on the failure and the consistency, and you compromise on the availability. But said that, as we have seen in the previous slide, that if there is a failure, it means there is a data loss, and these days no one can afford the loss of the data, because data is something key to any organization. Data is the new oil, right? So if there is no oil, there will be no motors, right? There will be no vehicles. Similarly, if there is no data, organization will cease to exist. They will not work more efficiently, right? So first of all, the basic thing is that no organization or no system can compromise on the allowing the failure. So this comes out of scope. So every company, every organization, every system, they cannot tolerate the failure. So this thing we definitely have to take care of. So there is no compromise on the failure. So now we are left with only these two. So ideally, the cap theorem says that if you are designing a system, you have to choose between these two, whether you want to have a highly available system or you want to have a highly consistent system. If you have a very highly consistent system, it means that the state of all the nodes will be the same, right? Right. So state of all the nodes will be same. Now, in order to maintain the state of all the nodes to be same. So, for example, if there is a client, whenever it is making a write request here, say for example data D, you have to write a sync request to another node and the another node, and wait for the write to complete, and then only you return back the response to the user. So we have to compromise sometime on the performance, sometime on the availability. So for example, if this write is taking too much of time, so this may do some kind of network timeout can happen, and system may not be available to the users. So what it says on a high level is that if there is any distributed system, at a time either it can be highly available, or it can be either consistency. So you have to choose between them. Either you have to choose this or you have to choose this. So I'll try to give you some practical examples when to go for availability and when to go for consistency, right? So for example, you have a kind of application which is something like banking, right? Where the data integrity is very important. The data has to be very consistent. You cannot have the two different kinds of data, right? In those kind of system for which the data, the data quality, the data integrity is very important, you should go for a high consistency. You should go for the high consistency, right? But if there is some kind of system in which you can still live up with some kind of stale data, even if you do a dirty read, you don't worry. So for example, say Facebook, okay? So in the Facebook, suppose even if somebody has made some update and you are not able to get it very fast, at the same moment of time, it's coming to you after some moment of time, or maybe you visited somebody's profile and you're still seeing the stale information there, you can still live with it, right? It's not something that we can which affect you very much, right? So in these social networking kind of places where the data integrity is not that great, but the most important thing is it should be available all the time, right? Because social network has become so much part and parcel of our life that we do spend a lot of time on that. And if it is not available, right, it might become tricky. People can move from Facebook to some other networking sites, right? So because of which the availability is highly important in the case of a website like Facebook. So I'll go with the case of the high availability. So depending on what kind of application that you have to deal with, what kind of application that you're trying to build, if it is a highly data integrity centric application, go with the high consistency. It is something which you want the availability to be very high, you have to go with high availability design. But failure you can never compromise. So out of the CAF theorem, which is say that you can either have CA part, or either you can have CP part, or you can have the AP part. What I say is that you cannot compromise with the the partition tolerance. So this you always have to take care of. So you always have to do a trade-off between the consistency and the availability. Out of these two, you should pick one, that whether your system should be highly available or your system should be highly consistent. I hope this is clear with the CAP theorem. And with this, now I feel we have made a strong foundation and the strong base, understanding what distributed system is. We have understood why do we need distributed system, what is the problem that is trying to solve, and how it evolved from the old way of storing the data to the new way of distributed way of storing the data. And this laid the foundation to the next big thing, which is known as big data, big data. So now let's talk about what is big data. Okay, as the name suggests, the big. Now this big is very subjective definition. Something which is big for you may not be big for me, right? And something which was big like 5 years back may not be big now. So for example, maybe like 10 years back, RAM of say 1 GB RAM was a big thing, right? But these days even your phone is having 4 GB of RAM. So something again, something when you call something is big, it is all in the context of who is talking what and at which frame of time, right? So just saying something is big doesn't make sense. So a data will be called a big in terms of following things: in the terms of the value, in the terms of variety, in the terms of velocity, in the terms of veracity, and in the terms of the volume. So let's try to talk one after the another. So a data is said to be big if after analyzing that data it can bring lots of value for you, right? A data which doesn't bring any value, doesn't holds any importance. There's no point you will go and store and spend so much of effort and money and the time in storing the data if it will not bring any value. So a big data is basically, when we talk about big data, we talk about so much of data which we have collected over a period of time, maybe from the IoT devices, maybe from the user activities on the different websites. Those data are relevant to us and it provides us some additional information so that we can take some kind of proactive steps in the future, maybe to make a better experience for the users, to provide a more better solutions to the customers and all those things. So big data, when we say big data, we also talk in the terms of value that it brings. The second thing is that variety. When I talk about big data, we just not talking about one one single direction. We are talking about the multiple dimensions, multiple directions, multiple areas in which we try to understand it, right? So when we talk about the big data, it consists of varieties of data, the different flavors of data, right? So that is about the variety. The velocity means at rate at which your data is coming in. It's just not that you're having a very stored amount of data, but rate at which your data is increasing, that is also important. Whether whether you're getting like 10,000 messages per second or you're getting like 10 million messages per second, these two are two different things. So we also talk about, when we talk about big data, we also talk about at what rate I'm getting the data. Okay. And then at the end of the day, we talk about volume, that how much data we are storing, at what rate we are storing data over a period of time, right? So whenever we talk about big data, we always talk in the terms of the value, variety, velocity, veracity, and the volume. And all these together comprises the big data. All this comprises the big data. In very nutshell, in very simple words, if I have to explain, a big data is amount of data that you cannot hold, you cannot store, and you cannot compute in a single machine. Okay, it's basically amount of data which you cannot store, storage problem, and you cannot compute also. So both of things cannot be done on a single machine. Single machine, if you try to do this, you cannot do it. So this is known as a big data. So basically, to solve any big data problem, to handle any big data, we need to have some kind of distributed computing into the place. So this is about the big data. So let's try to talk about, what are the next thing that we're going to cover into the big data tech space, and what all things are there in the big data tech space. So basically a big data is based on, the Hadoop pipeline, and Hadoop has basically two layers. As I said, we are only solving two things. One is the storage, right? And the another one is computation, right? So the storage part is being handled by something called as SDFS, and the computation part is being held by something known as the MapReduce. Okay, so as you see in this layer, Hadoop has something called SDFS. So this is the data storage layer. Then we have something called yarn. As I said that, a big data or Hadoop is nothing but basically it's a cluster of machines. So machine 1, machine 2, machine 3, machine 4, right? So there are different machines which should have to be connected to each other over the network, right? And they have to keep on communicating among each other. So how this whole communication between the machine happens, or how they keep on communicating over each other, these all happens over the network. This all happens over network, and there should be someone who manages it. There's something which manages this, and who is that manager? It is Hadoop yarn. Okay, so it is the Hadoop yarn which manages all things. So yarn is yet another resource negotiator, and we'll be talking about it in the details in the coming more specialization on these topics. So Hadoop yarn is nothing but the cluster manager, right? And then on the top of the Hadoop yarn, we have something called MapReduce, which is basically deals with this computation problems, which deals with the computation problem. So MapReduce was one of the most native way of solving the computation problem in the field of big data. But as and when we made more advances, the more and more solutions came into the play. So one of the biggest one was the Hive, which brought the SQL kind of thing for doing the same MapReduce job. So Hive sits on the top of the Hadoop MapReduce. You write the queries in the form of the SQL, which get translated into the MapReduce. Then few other variants were also available, like for example Pig, for those people who are more fluent in writing the scripting language. The Pig was more like a script which you can write to again execute the Hadoop jobs. And there's something called Mahout, and then these days the Spark is the new rage, right? Everyone is using Spark because of the new kind of optimization that is brought into the picture, like in-memory calculation, DAG, catalyst optimizer, and all the features like Spark streaming, Spark SQL, Spark machine learning libraries like graphics and all this stuff. So Spark is another big hot topic which we'll be covering in the coming sessions, which was brought into the picture. And apart from that, there have been some kind of streaming solutions, some kind of text vessels like the Solar, Lucene, then the Storm was there, right? And then some kind of NoSQL databases, Cassandra. Zookeeper is again a kind of a keeper of the cluster. We have something messaging system called Kafka. So these are basically the different components that you will normally see when you deep dive into any Hadoop system. So this was all about, guys, the getting started with the big data. We have seen how and why the distributed system came into the picture. We started with with a simple server machine which was enough to do our solve our problems. But we see that as and when the storage and the computation demand increased, we first tried to vertically scale it. There was a limitation to it. Then we started doing the horizontal scaling, which was basically a foundation of distributed system. We tried to understand what a distributed system is, what are the problems with it, how it was initially solved using the replication, then what were the problems that was brought by the replication, right? And with that, we try to understood the CAP theorem, which was the basic to anybody has to understand if they have to understand distributed system. And then we move to this Hadoop ecospace, and we try to understand what are the different components, what are the things that we're going to cover in the future sessions. So with this, I think you guys have a solid understanding now that how we made a transition from age when we had used to store all the data and the computation on a single machine to today's age in which you use a cluster of thousands of machines to do the computation. I hope you guys like it and really got benefited from this. If you really like this, and if you want to get notification about the more such videos, more such courses, please do like, subscribe, and share our channels. And please write in the comments if you have any kind of doubt. Please feel free to write in the comments, and we'll be more than happy to help clear all the doubt of yours. Thanks a lot guys for hearing me out and staying there and learning about the Hadoop thing. Thanks a lot.